Chapter 9 in your textbook is entitled Molecular Geometry and Bonding Theories. Now, for our purposes, our discussion is going to be based on the concepts of molecular geometry as well as electron group geometry, understanding the differences between the two and how electron group geometry can give rise to molecular geometries. Now, up to this point, we have a basic understanding as to how atoms bond to one another, but we don't necessarily have an idea as to the shape of molecules. Take, for example, water and carbon dioxide. Each of these molecules involves two atoms of the same type bonded to a central atom of a different type. Yet and still, we're going to find that they represent two different molecular shapes. A carbon dioxide molecule is linear in shape, while a water molecule is bent. Now, we may not have a good understanding or grasp on why that is, but that's because Lewis structures cannot give an indication of molecular geometry or shape. They show the bonding scheme, they show the non-bonding electron pairs, but they do not indicate shape. However, we can use Lewis structures as a tool in order to determine the shape or the molecular geometry of molecules. At the bottom of the slide, we see 5 different molecules in which we see several, 2 or 3 atoms connected to a central atom. In the first instance, we have carbon dioxide, followed by sulfur dioxide, sulfur trioxide, nitrogen trifluoride, and chlorine trifluoride. Now, while there may have been some similarities in those previous molecules in terms of atoms that were bonded to the central atom, there were significant differences. The primary difference lies in the bond angles as well as the bond lengths of those molecules. The bond angles help determine the shape of a molecule. Well, fundamentally speaking, let's think about electrons. Electrons are what form the bonds. But electrons don't like one another. Electrons tend to repel one another. Well, we know that electrons that pair up have to occupy the same space. But electrons that aren't paired up, or electrons in different electron pairs, have no reason to want to be near one another. Electron pairs are going to repel one another. Electron pairs are going to want to be as far apart from one another as possible. It is from this that we can determine the shape of a molecule. And the foundations of these concepts lie in what we call the valence shell electron pair repulsion model, also known as VSEPR. Now, to understand the shapes of molecules, we first need to understand the nature of the electrons that are surrounding our central atom. Around a central atom, we can have many types of electron orientations. We can have lone pairs. We can have single bonds. We can have double bonds. We can have triple bonds. And in some instances, we can have a single or lone electron that is unpaired in a non-bonding pair. Well, these areas around a central atom where the electrons are found are called electron groups or electron domains. If you will look at the bees represented on the left and right of our central atom, you will note that they have 4 electron groups around them. Each of those bees has 1 single bond and 3 lone pairs. The A, our central atom, similarly has 4 electron groups around it. 2 single bonds, 1 double bond, and 1 lone pair. Atop this structure, the lone B that is double bonded to our central atom only has 3 electron groups around it. 2 lone pairs and 1 double bond. The fundamental principle behind valence shell electron pair repulsion theory is that electron groups tend to repel one another in such a fashion that they minimize the repulsion between them. In other words, the electron groups want to be as far apart from one another as possible. If you look at the images on the right-hand side, what has been mimicked are electron groups being represented as balloons. So if we have a central atom, and that should be seen as the center of the balloons, or where the balloons come together. If you have 2 electron groups around a central atom, in order to maximize the distance between them, they're going to be found on either side of the central atom. If you have 3 balloons, as is seen in the second image, in order to maximize that distance, you're going to see the balloons orient in a triangular fashion. If we introduce a 4th balloon, things get a little more complicated. In the first 2 instances, the electron groups resided in the same plane. But in the 3rd instance, where we introduce a 4th electron group, we don't see a 90-degree orientation. In other words, we don't see an up, down, left, right orientation in order to maximize the distance between these electron groups. Instead, we see a 3-dimensional orientation that suggests that electron groups can maximize the distance between them by going into a different plane. And this is going to speak immensely towards the geometry of electron groups around a central atom. Now, Lewis structures can be quite deceiving. If I were to draw the Lewis structure for methane, for ammonia, and for water, we would see that in each instance we have 4 electron groups around our central atom. In the case of methane, we have 4 single bonds. In the case of ammonia, 3 single bonds and 1 lone pair. And in the case of water, 2 single bonds and 2 lone pairs. Now, the electron group geometry, or the electron domain geometry about the central atom, is going to be the same for all 3 of these molecules. But the molecular geometry is going to be different. And we'll talk in a moment about the differences between molecular geometry and electron group geometry. Since all 3 of these have 4 electron groups around the central atom, then they can be equated to the balloons that we saw on the previous slide, where we saw 4 balloons going in and out of the plane. Well, in order to better visualize what these electron group or electron domain geometries look like, I've presented a table. In this table, we see what a central atom looks like with respect to 2, 3, 4, 5, and 6 electron groups around it. In order to determine the electron group geometry, we need to count the electron groups around the central atom. Now, once again, remember that an electron group is the same as an electron domain, so those terms can be used interchangeably. If around a central atom we find two electron groups or two electron domains, then in order to maximize the distance between them, as we saw with the balloons, we would see a 180-degree separation. Since now the electron groups with respect to the central atom all fall in a straight line, then we would say that the electron group geometry would be linear. In the case of three electron groups around a central atom, we saw that the electron groups would be oriented in a triangular or a trigonal fashion around our central atom. The bond angle between electron groups would be predicted to be 120 degrees. And since the triangle all falls in the same plane, we would call the electron group geometry trigonal planar. When we see four electron groups around our central atom, we saw the bulging of the electron groups out into a different plane. In order to maximize the distance between the electron groups, we find a bond angle of 109.5 to be predicted for all bond angles. It's not that three of these electron groups fall in a trigonal plane and one of them does not. That's not the case. All four electron groups are repelling one another equally in this scenario. And so ultimately what we see is a bulging in and out of the plane with respect to all of the electron groups. If you'll notice the structure that can be drawn by connecting each of the electron groups, it looks like a four-sided pyramid. We can see the front and the side of it. You can imagine that there is a back and a bottom. So with that said, the four sides or the four faces of this structure would be deemed tetrahedral. So the electron group geometry for this would be tetrahedral. Now the next two groups that we look at involve atoms with more than 8 valence electrons around them. You'll remember an exception to the octet rule involved those molecules or ions where the central atom had more than 8 valence electrons around. Well, in these instances, we can have 5 electron groups or 6 electron groups. In the case of 5 electron groups around the central atom, the electron group geometry designation would be trigonal bipyramidal. In order to understand how these electron groups are oriented, imagine that 3 of the electron groups exist in a trigonal plane, separated by 120-degree separation. The other 2 electron groups are in a different plane perpendicular to the trigonal plane. So if you draw a structure that connects all 5 electron groups, it will look similar to a tetrahedral in that atop it we see a front, a side, and a back. But on the bottom, we would similarly see a front, a side, and a back. And the bottom of the top structure meets the top of the bottom structure. So it's essentially putting two pyramids together, which is where the term bipyramidal comes from. Now, if we imagine the bond angles for the atoms in the trigonal plane, they're going to have bond angles of 120 degrees. But from the perpendicular plane, we're going to see bond angles of 90 degrees. Lastly, when we find 6 electron groups around our central atom, as would be the case in something like sulfur hexafluoride, we're going to see an octahedral structure. We find 4 electron groups in a single plane, all 90 degrees apart from one another. And then we find 2 electron groups in a plane perpendicular to that, which also represent 90 degrees worth of separation. The term octahedral refers to an 8-faced structure. So if you look at this structure by drawing the lines connecting the electron groups, you will find that there would be 8 faces to that structure. Now that we've established electron group geometry, we're going to use this as well as the Lewis structure in order to determine the molecular geometry. The difference between electron group geometry and molecular geometry is simply that electron group geometry deals with the electron groups around a central atom, while the molecular geometry deals with the atoms that are around a central atom. So if we have lone pairs, the electron group geometry is going to be different than the molecular geometry, because lone pairs are not connected to another atom. So the steps that would be required to determine the molecular geometry involve drawing the best Lewis structure for the molecule or the ion in question. We determine the electron group geometry. And then we use the arrangement of the bonded atoms in order to determine what the molecular geometry truly is. Here we see an instance of ammonia. Ammonia, which has 4 electron groups around it. Well, if there are 3 atoms of hydrogen connected to the nitrogen, that means that there is one lone pair that is represented in this structure. With a tetrahedral electron group geometry, we see the bond angles would not be 90 degrees, nor would they be 120 degrees. We would expect a predicted 109.5 degree separation between these bonds. Similarly, we would see that same bond angle distanced between the atoms. So we would expect that the hydrogen, nitrogen, hydrogen bonds would be separated by that 109.5 degree angle. Now that's a prediction. Ultimately, when put into practice, we're going to find that the bond angle is not nearly that large. Well, if our electron group geometry is linear, then there's only one possibility for the molecular geometry, and that's linear as well. If the electron groups are going to try to get as far apart from one another as possible, and those electron groups are connected to terminal atoms, then those terminal atoms are going to be at the ends of those electron groups. So if we consider the orientation of the atoms, they would all fall in a straight line as well. It should be added that if there are only 2 atoms in the molecule, then the molecule will be linear no matter what the electron group is. The shortest distance between 2 points is a straight line. So if you ask me the shape of a molecule that has 2 atoms in it, well, it's got to be a straight line or linear. In the case of a trigonal planar electron group, we see options with respect to the molecular shape or the molecular geometry. If all of the electron groups are bonding electrons, single bonds, double bonds, triple bonds, then the electron group geometry is going to be the same as the molecular geometry. And that holds true for whichever electron group geometry we're speaking of. But specifically, Here we see a trigonal planar situation, as well as one that we call bent. In the case of an electron group geometry where all of the electron groups are bonding pairs, the electron group geometry is the molecular geometry, and that's trigonal planar. Boron trifluoride gives a representation, or is an example rather, of such an electron group geometry slash molecular geometry. But in the case of a trigonal planar electron group geometry that has one lone pair of electrons, then we would see a molecular geometry that reflected something slightly different. Again, remember, molecular geometry deals with the atoms and their connectivity, the shape of the atoms. So, if you look at the trigonal planar situation where the bonds would seemingly be 120 degrees from one another, then we wouldn't see the three atoms in the nitrite anion listed here in a straight line. Instead, they would be at an angle or bent. The lone pair electrons that sit atop the nitrogen are going to affect the shape of the molecule in a slightly different way, but we'll talk about that in just a moment. In the case of a tetrahedral electron group orientation, we see even more possibilities for molecular geometries. In fact, we also see different orientations about the central atom. They are tetrahedral if all of the electron groups are indeed bonding pairs. Trigonal pyramidal if we see one lone pair. Bent if we see two lone pairs. And again, linear if there's only one bonding pair. If there's only one bonding pair, that means that there are only two atoms, once again, giving rise to a linear molecular geometry. Now, trigonal pyramidal should not be confused with trigonal planar. In the instance of trigonal planar, all three atoms would fall in the same plane. Here we see a table that has examples of molecules with tetrahedral electron group geometries. If we have no lone pairs, then once again, all of the bonding pairs will represent all of the electron groups. So we would have a tetrahedral electron group geometry as well as a tetrahedral molecular geometry. The example that is given is that of methane. Once again, when we draw methane, the normal Lewis structure might suggest a left, right, top, bottom orientation, but that doesn't truly reflect the electron group geometry. You'll see that the darkened line represents a bonding scheme that is coming out towards you, while the dashed line represents a bonding scheme that is going back and away from you. So it gives a three-dimensionality to the structure. If we have one lone pair, then the orientation would be considered trigonal pyramidal. Notice that in the case of ammonia, we see the same electron group geometry around the central atom. The only difference between methane and ammonia is that whereas methane is connected to four things, ammonia is only connected to three. But the electron groups are still oriented in the same fashion. So rather than seeing the nitrogen and all three hydrogens in the same plane, we'll see the top lone pair of electrons repelling those electron groups, those bonding electron pairs, in such a fashion that the hydrogens are in a plane below that of the nitrogen. So instead, the atoms themselves, if you were to play connect the dots, would form a pyramid of sorts. So that is why the molecular geometry is referred to as trigonal pyramidal. And in the case of water, you can imagine the same electron group geometry, yet there are only two things that are bonded. So if we're talking about the molecular geometry, the orientation of atoms within a molecule, then the electron group geometry of of tetrahedral with two lone pairs simply leaves us with a molecule that has a bent shape, similar to that of the nitrite anion that we saw previously. Now, it's important to note that all electron groups do not repel equally. Non-bonding pairs have a greater sphere of influence about a central atom, and it's because they're not as localized. In a bond, the electrons must be between the two atoms that are bonded. But a lone pair has a much larger sphere of influence. It has a much larger area in which the electrons can reside. So with that being said, they can affect the repulsion even greater than bonding pairs. And that's evidenced in the series of molecules that we saw on the previous slide. Methane, where we see 4 bonding pairs, shows bond angles of 109.5, exactly what would be predicted from the tetrahedral orientation. Ammonia, on the other hand, has bond angles of 107 degrees between the nitrogen-hydrogen bonds. That means that the lone pair is pressing down even harder on the bonds, forcing the bonds to actually be closer to one another, forcing the nitrogen-hydrogen bonds to be closer to one another. And finally, in the instance of water, we see the lone pairs, again, pressing even harder on those bonding pairs, forcing those closer together, resulting in an oxygen-hydrogen bond angle of 104.5. Again, less than the predicted 109.5 for a tetrahedral orientation. We see a similar phenomenon when dealing with multiple bonds. Double bonds and triple bonds have more electrons between the two atoms. Therefore, their sphere of influence is greater as well. So in the case of the COCl2 molecule listed here, we see that the carbon-oxygen double bond has more of an influence on the single bond CCl bonds. They're pressing down, they're repelling one another even harder, forcing the carbon chloride bonds to be closer to one another. Now, when we go beyond the octet rule, those atoms, central atoms that can take on more than 8 valence electrons, the results are the two electron group geometries of trigonal bipyramidal and octahedral. In the case of trigonal bipyramidal electron group geometry, we have to make a distinction between the electron groups that are equatorial and that are axial. The equatorial ones would be the ones in the trigonal plane, while the axial ones would be considered on the top, the bottom, if you will, the plane that is perpendicular to that plane. Now, if we see lone pairs tend to occupy the equatorial positions in a trigonal bipyramidal electron group geometry. With that being said, we're going to see four different types of molecular shapes or molecular geometries: trigonal, bipyramidal, seesaw, T-shaped, and as always, linear. In the case of the phosphorus pentachloride molecule, we see all 5 electron groups are bonding pairs. So when that's the case, the molecular geometry is the same as the electron group geometry. We have a trigonal bipyramidal molecular geometry. But if we deal with sulfur tetrafluoride, we see one lone pair when we construct the Lewis structure. That lone pair is going to be found in the equatorial plane, and it's going to give us what we call a seesaw shape. In the case of chlorine trifluoride, we see 2 lone pairs in the equatorial positions, therefore giving us what we call a T-shaped molecule. If you turn that molecule on its side, then you could visualize it being called a T-shaped molecule. And lastly, if we have 3 electron groups that are non-bonding, then that would result in a linear molecule. Again, the 3 electron groups would be in the equatorial plane, leaving only the axial plane for our 2 bonding pairs. In the octahedral electron group geometry, all of the positions are essentially equivalent. But if we were to place lone pairs or assign lone pairs to a molecule when we were considering its molecular geometry, imagine placing those lone pairs in the axial positions first. With that being said, there are 3 unique electron, or rather molecular geometries for the octahedral electron group geometry. There's octahedral, square pyramidal, and square planar. In the case of sulfur hexafluoride, a molecule in which we see 6 electron groups around our central atom, and all of them are bonding pairs, the molecular geometry, as well as the electron group geometry, would be octahedral. But if we see bromine pentafluoride, in which we see 1 lone pair, the electron group geometry would be octahedral, but the molecular geometry would be square pyramidal. It would be a square base, as is seen in the equatorial plane, with a pyramidal orientation, because those lone pair electrons are going to be pressing with a different intensity on the remaining bonding pairs. Lastly, in the case of xenon tetrafluoride, a molecule in which we see xenon, a noble gas, participate in bonding, we see 2 lone pairs, and those 2 lone pairs we see found in the axial positions, leaving us with a molecular geometry of square planar. All 5 atoms all lie in the same plane in a square orientation. Now, these speak to molecules that essentially have one central atom. But sometimes we find ourselves dealing with larger molecules, molecules where we have multiple things bonded to multiple atoms. And in these instances, rather than looking at the shape of the molecule as a whole, we look at the molecular geometry around each atom. Finally, we want to consider the concept of the polarity of molecules. Remember, if there's unequal sharing between 2 atoms with regards to the electron density, that bond would be considered a polar covalent bond. But the molecule on the whole wouldn't necessarily be a polar molecule. For example, if we're looking at carbon dioxide, we see that each oxygen is pulling on the electrons from the carbon. So the electron density is being pulled away from the carbon in each carbon-oxygen double bond. But since the molecule is linear and we see electron pull in one direction of the same intensity as electron pull in the other direction, then those dipoles essentially cancel out. So we have to ask ourselves, is a molecule polar? Well, the first thing that we ask ourselves is it covalently bonded or ionically bonded? If it's covalently bonded, then we continue. If it's ionically bonded, then number one, we're not dealing with a molecule, we're dealing with an ion. And number two, we understand that there's going to be a difference in electronegativity that's going to give rise to the gaining and losing of electrons. So, are the bonds polar? If the bonds are not polar, then the molecule is nonpolar. If the bonds are polar, in other words, there is a charge separation, then we have to ask the second question. Do the dipoles balance out as they do in carbon dioxide? In the case of water, we don't see those dipoles balanced out. While they do pull in different directions, they're not being pulled in opposite directions. What do I mean by that? Well, I think that this final slide illustrates exactly what I mean by that. Carbon dioxide shows equal and oppositely directed bond dipoles. Whereas in water, we see the hydrogen-oxygen dipole being pulled up and towards the oxygen. The electron density is greater around the oxygen than it is around the hydrogens. But since these two do not cancel each other out, they're not moving in opposite directions, then there is an overall dipole for the molecule. In each instance, each bond is being pulled upwards. The electron density is being pulled upwards. So while the left and right component does balance out, since they are both being pulled upwards, there is an overall dipole moment that suggests an upward pull. And at the bottom of the slide, you can see a representation using colors to reflect electron density. Well, this wraps up our discussion of Chapter 9. I hope that you learned a little something from it. As always, good luck and stay safe.